So there are a lot of properties of continuity and continuous functions that we want to be able to utilize. And the first thing is something that's kind of obvious. If you have two functions and they're continuous at a particular value, right, any value, then the following functions will also be continuous at that same value. We use this all the time. So we use it in pre-calculus, we use it in calculus, etc. Because if you have, for example, a function that you knew is continuous, then if you multiply it by a constant, it's still going to be continuous. You can add up different continuous functions and string them along together, and they'll still be continuous. Same thing with subtraction. You can multiply them. You can take them to a power. And you can take the quotient, provided that that denominator is not equal to 0, which we were just using that little provided part to find the asymptotes and punctures in the graphs on the previous example. So that means that the following types of functions are continuous everywhere. So if you have polynomials, so just assume p of x and q of x are polynomial functions. So constants multiplied by x to a power, and then they're strung along together into multiple terms. So if you have that, they will always be always continuous, right? So this part is telling us all polynomials are continuous, period, the end. You never have to think about it. They just are. I actually mentioned that a couple pages ago as well. While you're on the subject, sine and cosine are also always continuous. And so are some of these other ones. These four we know have major issues, right? The trigonometric functions, you got to watch out. They have asymptotes. These four have asymptotes all over the place. So those you've got to look out. So let me just make a little note. These four, they're continuous everywhere. Let's highlight it in their domain. If you'll notice, in their domains, and that's the key, because these four functions here, for example, have lots of discontinuities because they have lots of values that are not in the domain, right? All the values that would make vertical asymptotes on these four. So these have, let me just say, infinitely many asymptotes. So watch out for those trig functions, those four in particular. The other ones are all okay. The other ones, it has to do with the way that they work and the way that they're restricted. But the other ones are all fine, and they're continuous everywhere because the top two are continuous all the time. And the bottom six, if you remember, they're very restricted. So you're basically only looking at the sections that they're continuous. There might be an exception to that. There might be a graph here or there. It depends on how you define them and how you graph them. But these don't have nearly the infinitely many asymptotes that the four up here do. Now the rational functions we've already known about. Those are continuous everywhere except where the denominator would be 0. So these are continuous except where the denominator equals 0. And we already saw that even if the denominator cancels away, because that canceling away, that dividing away, is not, it's changing the function fundamentally. It's changing it to an equivalent function, but not the exact same function. So anything that would make the original denominator equal to 0 would be an exception, would be a discontinuity point. And then, of course, we can never take, not in the real number systems. So these are continuous everywhere, except if you're talking about an even root of a negative. Except if you're taking an even root, like a square root or a fourth root or a sixth root or something, of a negative number. That's not allowed. That's forbidden. But other than that, they're continuous everywhere. All right, so this is just something to note. This is, you've actually used a lot of these properties all through pre-calculus when you were graphing in pre-calculus or graphing in algebra. When you were putting in vertical asymptotes, you were dealing with this. We would graph radical functions that have them have endpoints. That's this. We were graphing trigonometric functions and discovering these are like waves, and these ones have infinitely many asymptotes, etc. Exponential functions are fine, right? Exponential functions are continuous everywhere. So these ones right here are also continuous everywhere. Everywhere in the domain. Everywhere in the domain, which is everywhere, because the domain of exponential functions is anything. You can take any base to any negative power, any positive power, any fraction, no problem. So those are continuous everywhere. Don't have to think about it. Logarithms, however, are not continuous everywhere. Logarithms, you cannot take the log of 0, so they're continuous everywhere except you're not ever allowed to take the log, any log base a of 0, no log base a of a negative number. Those are forbidden, right? So other than that, you're continuous. Now, when a function is composite, so let's say we were going to take some combinations of these functions that we've been looking at. What we need is for the inner function, g of x, to be continuous at a, and the outer function, f, to be continuous at that output of g of a. Right? Then the composite function would also be continuous. And that applies to our limit definitions that we learned earlier in chapter 2 as well. If the function g is continuous at a and f is continuous at g of a, then the limit of that composite function is equal to the function of the limit. We learned that earlier in an earlier section. All right, so let's use that. This theorem allows us to interchange the order of limit and function evaluation. Note that the second statement does not claim g of x needs to be continuous at the input value of a. Got it. So they're saying if you want the limit of f of g of x, then you could find the limit for g of x, not saying that it's continuous there, but it's just saying if you find the limit for it, then you could find f of that limit. All right, so we're going to use that to do the next problems. So for this example, they want us to use the theorems for composite functions to evaluate the limit. So we're going to use that theorem that we just saw for composite functions and continuity and limits and all of that stuff to be able to do this. So keep in mind that for this particular problem, for the first one, this inner function right here, that's a polynomial, right? And since it's a polynomial, it's continuous at 0. So let me just write this. So this inner function, g of x, which is x to the 8th plus 3x to the 6th plus 1, is a polynomial. So it is continuous from negative infinity to infinity, right? It's continuous everywhere, including at x equals 0, because 0 is the interesting limit that I'm interested in. All right, now how does that help me? Well, I can use my theorem and can say, okay, well, since I know it's a polynomial and I know my inner function's continuous there, then I can actually take the limit as x goes to 0 of x to the 8th plus 3x to the 6th plus 1 and nest it inside my outer function, which is the 40 part. So I'm going to take the limit, instead of being of the whole thing, I'm just going to take the limit of the inner part, get that number, right? So I'm taking the limit of g of x right here, right? So, if you will, I'm taking f of the limit of g of x. So I'm just finding the limit of g of x part right here, right? Then I'm raising it to the 40th power. I guess I could put 40 in like a different color because that's the outer function right here. Okay, so, but we just said this is continuous everywhere, so, and it's a polynomial, so this is really no problem. We will just substitute 0 in for x. So I would get 0 to the 8th plus 3 times 0 to the 6th plus 1, which we all know that's 1, right? So this is 1 to the 40th power, which is 1. And there we have it. All right, now let's do the next one. So the next one's going to be a slightly bit more complicated. But you'll notice that you have an outer function and an inner function. Oh, I never actually mentioned what the outer function was on this one, but let me just mention. So g of x was right here. F of x would be x to the 40, right? So this was the outer function, and then that g of x was my inner function, right? So for this particular one, for letter B, the inner function's right in there. So it's this very elaborate g of x equals x cubed minus 2x squared minus 8x over x minus 4. And we can tell that that's continuous except at x equals 4, because 4 take away 4 was 0. So continuous everywhere except x equals 4. Okay, and then f of x is equal to the square root of x, right? That's the outer function right here. And then this is my inner function, g of x right here. This is my inner function. Okay, so according to our theorem, what I can do is I can take, instead of this, I can say, hey, instead of taking the limit as x goes to 4 of f of g of x, I can take the square root, there's my outer function, of the limit as x goes to 4 of my inner function. Now I know what you're thinking. You're thinking, well, but we can't have 4. If we put 4 in, we will substitute and we will get 0 because there's that denominator. And you'd be correct. If only you knew some tricks, algebra tricks, that would help you simplify it. Yes? So this would be the square root of, and then we'll simplify this inner portion. So that numerator factors. You can take an x out of every term. That'll leave you x squared minus 2x minus 8. Okay, and that would be equal to the big square root of the limit as x goes to 4, x times x minus 4 times x plus 2 over x minus 4. Oh, isn't that convenient? Because x minus 4 over x minus 4 makes 1. So this is equal to the square root of the limit as x goes to 4 of x times x plus 2. And that we can substitute into, right? Right here, we can substitute 4 into this. We couldn't up to this point because we would have had 0 in the denominator, and that's bad. But when we factored in and divided away right here, we end up with this term with no denominator anymore. Or, well, the denominator is 1, so that's kind of useless. So that would be equal to the square root of 4 times 4 plus 2, which would be 4 times 6, which is 24. So this is the square root of 24. If you want to reduce that, 4 goes into 24 6 times, so that's 2 square root of 26. Either one.